So this is the solution for example 30. The circuit shown switches a warning lamp on or off depending on the temperature. So we've got power supply, two resistors in series which form a voltage divider, this component which is the switching component, and a lamp. So this component P is a MOSFET. As the temperature increases, the resistance of the thermistor RT decreases. What happens to the voltage across RT as the temperature increases? So I'll answer that one down here. B, as the temperature increases, the resistance of the thermistor decreases. The voltage VT across RT will decrease. So temperature up, resistance down, TURD, that's your acronym to help you remember. On to part C. When the voltage applied to component P is equal to or greater than 2.4 volts, RV is adjusted until its resistance is 5600 and the warning lamp now lights. So we have to calculate the voltage across RV and the resistance across RT. So I'll just use this space here to gather the information together. So I have the resistance on RV, I have the resistance of the variable resistor, is 5600 ohms. RT, I need to work that out eventually. The voltage on the thermistor is 2.4 volts. Now I know that because here it says that the voltage applied to component P must be equal to or greater than 2.4 to switch it on. So component P is controlled by this voltage in here, which is the voltage across the thermistor. So the voltage on the thermistor must be 2.4. And the voltage on the power supply I also know, and that is 12 volts. So to get to the first part of C, the voltage across RV, we can use simply the fact that the 12 volts here must be equal to the voltage across these two components added together. So in other words, the voltage on the power supply must be equal to the sum of the voltage on the thermistor plus the voltage on the variable resistor. So power supply is 12, the thermistor is 2.4, which means that the variable resistor must be the difference between the two of those, which is 9.6 volts. So that's the voltage on the variable resistor. Voltage across RV. So the last part of this calculation is to work out the resistance of RT, and for this one you're going to need to do a potential divider calculation. So we're going to work out the resistance of RT as the ratio RT divided by the resistance on the variable resistor. That must be equal to the voltage across the thermistor divided by the voltage on the variable resistor. So that's your voltage divider equation, but instead of using R1 and R2 and V1 and V2, I'm using these symbols. So then I carefully substitute in what I've got. So RT, what I'm trying to work out, divided by 5600 must be equal to 2.4 divided by 9.6. So to solve this for RT, multiply both sides by 5600. So RT equals 2.4 divided by 9.6 times 5,600, which works out as 1,400 ohms. Last part, the temperature of RT now decreases. Will the lamp stay on or go off? And you must explain your answer. So we can make a statement that the lamp stays on, but we must explain it. If we don't give an explanation, we'll get no marks, guaranteed. The lamp stays on because as the temperature decreases, that means that RT must increase in its value. And because it's in a voltage divider, when the voltage across RT increases, that will force the voltage on the component P to increase above, still further above 2.4 volts. And that will ensure that the MOSFET stays on. Okay, so that's that one. And now we're on to example 31. Name component X. So component X is a transistor. What is the purpose of component X? So at the National 5 level, we always say that a transistor acts as an electronic switch. The dark room is opened and the light level increases. Explain how the circuit operates to sound a buzzer. So basically, as light falls onto this LDR here, the light level goes up, its resistance will go down, which means its voltage share will also drop. But if this voltage goes down in the voltage divider, this voltage must go up, even though that we're not changing that resistance value. That voltage will increase. If that voltage increases above 0.7 volts, that will switch on the transistor and complete the circuit, allowing the buzzer to sound. So that's your explanation there. Last part is to calculate the current flowing in the LDR. So here we've got the light level increasing to 80 units. What you need to notice there is that when you're at 80 units, then you're looking at 2,500 ohms. So for this one, I'm going to start gathering together the information I have. And the first thing I've got is RV. It's 570 ohms. And then the resistance on the LDR, which will be 2,500 ohms. And I also know the voltage on the supply, which is 5.0 volts. So the way to do this is to realize that if you add these two resistances together, you'll get the total of the two resistors in series. And then you can basically apply Ohm's law to calculate the current flowing through here, which will be the current flowing through the LDR. So the total resistance, RT, equals RV plus R LDR, which is 570 plus 2,500, 3,070 ohms. Then simply apply Ohm's law. I equals V divided by R. So in this case it's the supply voltage divided by the total circuit resistance. So it's 5.0 divided by 3,070. So 5.0 divided by 3070, which gives me 1.62 times 10 to the power of minus 3. 1.63 times 10 to the power of minus 3. I need units, and I need to think about the number of significant figures. So it looks like 2 significant figures. So that would really be 1.6. And I could just say, well, it's milliamps.